Hello, grade 12s. We're here to actually work through an example on rotating frames of reference, specifically pertaining to artificial gravity. So there's lots of different uses for the role of inertia and what that has to do with circular motion problems. You can read through several of them in your textbook, but I'm just going to go through an example with artificial gravity. Now, space travel can have detrimental effects on humans as we evolved on Earth. We are designed to live and survive on Earth and ideally flourish here. Our entire body system is designed to work with gravity. So without gravity, we're in big trouble. Now, we know that the force of gravity due to Earth on us is our weight. And we could calculate it by doing our math, taking our mass and multiplying it by 9.8 meters per second squared, or 9.8 newtons per kilogram near Earth's surface. But our interpretation of our weight, or our apparent weight, is actually a result of the normal force acting on us. Now, this can give us some very unique sensations. Under some conditions, if our normal force is bigger than the force of gravity, we will feel heavier. If the normal force is less than the force of gravity, we're going to feel lighter. And if there's no normal force acting on us at all, we get this really unique sensation of weightlessness. Now, if we have a spacecraft that's actually a rotating frame of reference, we can manipulate the speed of rotation of that spacecraft to make our normal force similar or equal to that of gravity. And since our normal force is our apparent weight, that means we would appear to still be experiencing gravity. Now, our spacecraft is designed to be a circle, like we have right here on our disk, and I've replaced where Larry was with this little astronaut person. Now, if I spin the disk, we know from our demonstration with Larry that that person is going to experience force towards the center of that circle, which is causing that rotational motion, but they also, from within their frame of reference, feel this outwards push. And that's going to give us a free body diagram very similar to what we see right here. So there's that outwards push that's the centrifugal force, and then the inwards push, which is the normal force. So unlike the problem with Larry, there's actually going to be a floor here, which is going to stop that astronaut from flying off of the spacecraft. Now, from an inertial frame of reference, we know that there's only the normal force, and that interpretation of that outwards push is just the result of inertia. But the sensation of that force being there, that outwards push, is very, very real to this person right here, our little astronaut. So let's have a look at an example and see if we can't put some numbers with this. So this is the example that we're going to work through. I had to do a little bit of research here to make it accurate. So we've got a spaceship from a popular, very old, I'm guessing retro now, video game of Halo. And this spaceship was unique because it actually had a central ring which rotated. Now, the radius of that central ring is about 150 meters. This is on that spaceship. And it could vary its rate of rotation to simulate gravity here on Earth, or actually give you situations where gravity would be increased, which could be beneficial for training, or where it's decreased. Now, what we're going to do is we're going to calculate the period of rotation required to mimic Earth's gravity. So to give us a normal force or an apparent weight, which would be equal to our weight here on Earth. So let's take a minute and look through those free body diagrams again and see what we have to work with. Now, if you're on that non-inertial frame of reference, you're going to experience that outwards centrifugal force. And this would be similar or take on the same sort of role that the force of gravity would. But you don't go crashing through the floor of the spaceship because there is actually a floor there to stop that. And that is going to give us that normal force. Now, from an inertial frame of reference, we would explain this force just as a result of the inertia of the occupants of the spacecraft, which means we only have the normal force, which is causing that rotational motion. So to analyze this, we're going to work with our inertial frame of reference. And we're going to see that because the spaceship is actually rotating, the centripetal force which is equal to mv squared over r, and that's from Newton's second law, is also going to be equal to that normal force. And these are all just the magnitudes that I'm working with, so it's understood that the direction will be towards the center. So that's what we're looking at here. Now we're going to take these two different equations and we're going to actually set them equal to one another. So we'll have that the normal force is equal to mv squared over r. Now what we want to have happen is we want our apparent weight, which is Fn, to be equal to our actual weight here on Earth, which would be Fg on Earth. And on Earth, we know that the force of gravity acting on us, or our actual weight, is whatever our mass is multiplied by 9.8. I always save my units until the end. If you want units in there, meters per second squared for acceleration, or newtons per kilogram if you're going with gravitational field strength. So we're going to take this, which is equal to the normal force, and this, which is equal to the normal force, and we're going to set them equal to one another. So we've got m times 9.8 is equal to mv squared divided by r. Now we can see that we have this generic mass value on either side. That's going to cancel out. And what's good about that is it means regardless of the mass of the astronaut or the occupant of this spaceship, they're all going to experience that same force of gravity that they would here on Earth. Now, we're going to work with or try and figure out the speed first and then take that next step towards the period. So the speed, if we rearrange this equation, is going to be the square root of 9.8 multiplied by the radius, where the radius was 150 meters. Okay. And if we calculate this, we're going to get 38. And that would be meters per second. So carried a few extra digits, just so that we can go ahead and use that in our next step. Now the question didn't ask us for the rotational speed, it asked us for the period of rotation. So we need to get from speed to period, or time. And we might remember that time is just distance over speed. And the distance for something experiencing circular motion is equal to the circumference, which is 2 pi r. So the period is 2 pi r, which is that circumference, divided by the speed. So if we substitute all of our values in SI units, 150 for our radius and 38.3406 meters per second, we're going to see that the period of rotation is about 25 seconds. So that's putting things into perspective a little bit here for us. That's pretty darn quick. And that is how we would solve this type of problem.